Okay. All right, today is Thursday, January the 26th. Today we're going to be going over the three most current AP questions dealing with kinetics. Okay, years 2014, 15, and 16. All of those are available online if you want to look up on the College Board along with the answers. Okay, but we want to discuss this. Okay, so this is going to give you an idea of what you need to know about kinetics. All right, when we actually start taking some practice exams, we'll look at the multiple choice and kind of see how things are asked in the multiple choice section. But and on the test you take next Thursday, you'll get a little bit of a taste on the type of questions you'll see in multiple choice questions there as well. But your class test is next Thursday. Okay? I know you're not going to be here, but you'll just have to make it up. All right. So, the first question, this is year 2014. This deals with, I'll leave this right here. Okay? This deals with the half-life. So notice that we're not given concentration, we're not given, the normal table. This is kind of a different type table. And I wanted to use this question just to kind of point out how they use the whole idea of half-life. Okay? And so the only thing that we can see here is that the temperature is constant in these first three. In number 4, it is increased to 365. So that's going to change just about everything. It speeds up the reaction. It's going to change the half-life. It's going to change. It doesn't change the order of the reaction, but it does change the rate of the reaction. And therefore, it'll change the half-life. But if the half-life remains constant, as you change concentrations, as you change volumes and all the different things, if the half-life is constant, what does that mean as far as the order of the reaction? It's first order. If it's second order, it's actually going to be decreasing. It's 1 over the concentration, the way the half-life equation is. And it's not even given on your equation sheet that you have for second order, which means that you probably aren't even going to have to worry about it. But if the half-life stays constant, we know it's first order. And that's actually your justification. So the reaction is first order. Explain how the data is consistent with first order reaction. The data is consistent because the half-life stays constant for as long as temperature is constant, which is consistent with a first order reaction. Okay? So that's how you know. I mean, that's more of a memorization thing than it is even a concept thing. So then on B, calculate the rate constant. Well, then if you go to your equation sheet, dealing with half-life, you don't have, normally we would say rate is equal to K times the concentration. But we don't have any of the concentration stuff. So we can go simply to a marker. What's the equation for half-life for first order? T1 half is equal to 0.693 divided by K. Now, if you recall, I derived this equation from the integrated rate law the other day. Okay? But it's nice to know that it's derived from the integrated rate law, but it's a lot easier just to plug it into here.
Can I take that?
Yep. Okay. It's on the equation sheet. It's there. So we're going to solve for K. So obviously K is going to equal 0.693 divided by the half-life, which is 0.693 divided by 100 seconds, right? 100 seconds. So K is equal to 0.00693, and the unit is just going to be per seconds, or seconds to the minus 1. Okay? So, a lot of students missed this one that year, just because we didn't go to this. So I want to kind of stress that this would have been easy money, easy points, plug it into the simple equation. So then C, okay, C is going to tell us, calculate, is the initial rate of the reaction in trial 1 greater than, less than, or equal to the initial rate in 2? Okay? So when we come here in 2, what's the difference between 1 and 2? The pressure. What does that mean about the molecules in 2? There's a lot more of them. They're in the same volume, 2 liters, so we have double the number of molecules, which really means we have greater concentration, but it's going to increase. I heard somebody say more what? Way more collisions. And more collisions means?
A greater probability of proper orientation, so reactant bonds and breaking bonds.
Okay, that's the perfect answer right there. Okay? We need to just learn that. It's not a little catchphrase, it's a long one, but we just need to learn. Well, hey. We'll change the name of our chemistry class to catchphrase. Okay?
I'm down.
Yeah. So, the increased pressure, reaction 2, we expect the rate to be faster because the higher pressure means there's more molecules present in the container, which is going to increase the number of collisions, which increases the probability of having the proper orientation to where reactant bonds begin to break and product bonds begin to form. That's what you want to write. And then D, the half-life of the reaction in trial 4 is less than the half-life in trial 1. Explain in terms of activation energy. So what did we do differently in trial 4? Increase the temperature. Now, how does that affect our activation energy? Does it lower the activation energy?
No.
What does it do?
It gives the molecules more energy to get it.
Okay. Does it give all molecules more energy?
A higher fraction.
A higher fraction. And what graph kind of demonstrates that? The Maxwell-Boltzmann temperature distribution graph. Okay? So if you really wanted to be, again, if you wanted to be gung-ho, if you want to be gung-ho, we have our Maxwell-Boltzmann temperature. This is fraction of molecules. This is energy. Okay? So at T1, it looks like this. And let's just say that this is EA. So we have this fraction of molecules at T1. 350. So as I increase the temperature to T2, 365, what's going to happen? What's the graph going to look like? Flatter, always flatter, and to the right. So now it's going to look like this. So here's T2 is equal to 365. So now we have a much greater fraction of molecules that have enough energy to overcome EA. You can put that right here as part of your answer.
That's all I
But you need to put it in words as well. Okay? But this is the graphical explanation of saying that at the higher temperature, a greater fraction of molecules will have enough energy to overcome EA, which will cause the reaction to go faster. Plus, what does increasing the temperature? What else does increasing the temperature do? Speed them up, which does what?
Powerful collision.
Increases the number of collisions, which
A higher probability.
which increases the probability of having proper orientation to where product bonds begin to form and reactant bonds begin to break. Okay? All right. So, we need to be able to relate this graph to EA. Now, what does adding a catalyst do to this graph? Low, but on this graph is activation energy. What's it going to do with this? It's going to move activation energy to the left, make it take less energy. Okay? So by moving it to the left, it does the exact same thing by adding a catalyst. It increases the fraction of molecules that have enough energy to overcome EA. Not necessarily by giving them more energy, but by making the energy required less. Okay? So on our other graph, it's going to lower the hill. On this one, it moves EA to the left. So we need to be able to do that on both graphs. You good with that? You going to live and not die? Any questions on this one? Any questions there? Hey, what this should be doing to us is giving us confidence. Hey, I can do this. These questions are doable. These are the most current questions. Okay. Now, once again, listen. I only have 15 minutes left, and then we're going to have more. Yeah, I'm leaving at 1:45, and then we're going to finish working on these problems, and if you want, you can do the rest of them. Okay, if you finish. Okay? Hey, and again, reminder, tomorrow we're bringing Princeton Reviews. I'm going to try and send a Remind Me out. Justin can do it if I forget. Okay?
So I'm not here on Thursdays.
Okay, or you can just keep it in your backpack and lug it around and get in shape. Okay? So, all right, so listen. One of the challenges of AP Chemistry now is the way that they're modifying the test is they're making it very wordy. Okay? It's kind of like ACT. I don't know, they're just, because they make it sound like, you have to be able to unwrap the question and all that. So, part of the challenge for us is to, number one, not look at this question and just get overwhelmed and intimidated right off the bat by how long it is. Okay? And by the number of words. So we just go through and we isolate it, because realize the kinetics questions, there are a few, there's a small category of questions that you're going to get to ask. Yes, sir?
So time is a factor. Do you recommend reading the question?
Yeah, almost definitely. Because you need to look for key words to direct you as far as what they're asking, what it's about. I would probably underline or something the key words in there as you go. First order. If you see first order in there, because that's going to direct me to my integrated rate law or my, just know what are we measuring the rate of? Is it the formation of this? Is it the disappearance of that? What is it measuring? Okay. As soon as I see these graphs, before I go to, for me, I see the graphs. The first thing I'm going to do is say, okay, which one's a straight line? It's this one, so I know it's first order. Okay. Now, so I know we're in first order, but I think I think you have to figure that out. So, then I'm going to look. Blue food coloring can be oxidized by household bleach, which contains OCl minus. The hypochlorite ion. It's actually sodium hypochlorite, but the sodium's a spectator. It's the hypochlorite ion that is the active ingredient in bleach. To form colorless products as represented by the equation above. A student used a spectrophotometer. Now, we've used that. That's our Spec 20. That's what we did our Beers Law Lab. Okay? Set a wavelength at 635 to study the absorbance of food coloring. Why 635? What determines what wavelength you use? What color it is. And how do you know what wavelength to use based on the color? What do we look for? Where it absorbs the most or the least? Okay, remember we had the graph and we on that handout on Beers Law. It's always the maximum amount. Okay, and just so you know, Beers Law is a classic lab that they love to ask questions about. Okay, so it's always where you have the maximum absorbance. So when the graph of wavelengths versus absorbance, where the peak is the highest, that's where you're going to set the wavelength to. And every color is going to have a different wavelength as far as what it's going to absorb at. And that's why we had to change it when we went from the pink solution to the blue solution. We had to change the wavelengths for the cobalt and the copper. Is that ringing a bell, kind of, whatever? We do labs, not just for the fun of it, but because we need to learn about the chemistry as we're doing it and how to use the equipment. So, that's our Spec 20. Okay, the absorbance of the food coloring over time during the bleaching process. In this study, bleach is present in a large excess, so that the concentration of OCl minus is essentially constant throughout the reaction. Okay? The student used data from the study to generate the graphs below. Okay, so first, based on the graphs, what are the reaction? So we know that. And what's the explanation? Because the graph of ln of absorbance versus time is linear, that indicates it's a first order. And if you want to, again, be gung-ho, it's based upon which form of the rate law? Based upon the integrated rate law. Okay? So, because this is all, remember, it's derived from the y equals mx plus b is the integrated rate law, is how that comes out. Okay? So now, this one, you guys, a lot of y'all ask me questions about this one. It says the reaction is known to be first order with respect to bleach. In the second experiment, so what if it's first order overall, what's the order with respect to the dye? 0. Because otherwise, it would be a second order reaction, and this wouldn't be linear. Okay, so it must be 0 order in terms of the dye. But they're telling you in terms of the bleach, it's first order. In a second experiment, the student prepares solution of food coloring bleach with concentrations that different, so it's no longer in large excess. When the solutions are combined, the student observes that the reaction mixture reaches an absorbance near 0 too rapidly. So the reaction is going too fast. So in order to correct the problem, the student proposes the following 3 possible modifications to the experiment. So, increasing the temperature. If it's going too fast, what do we need to do to the reaction? Slow it down. Will increasing the temperature slow it down? Now that always speeds it up, right? So then it's between changing the concentration of the food coloring or changing the concentration of the bleach. Okay? Well, bleach is what's causing the oxidation, right? So if I increase the concentration of the bleach, it's just going to go faster again. But if I increase the concentration, keep the bleach the same, but increase the concentration of the blue, what does that mean as far as what the bleach has to do now? It has to react with more blue molecules to make the color disappear, right? So that's just going to take longer. So that's the only one that can increase the rate of the reaction, is by increasing more of what it has to oxidize. Since the bleach is the thing doing the work, increasing it's going to speed up the reaction. Now, and again, because it's kind of 0 order with respect to the blue, increasing the concentration doesn't really speed the reaction up. So that's kind of something that you can kind of pick up from the fact that it's first order with respect to the OCl minus. Because we know the overall reaction is first order, we know it's 0 order with respect to the blue, so increasing its concentration doesn't increase the rate. But just by logic, you would have to say that. You don't have to say that to get full credit. Just by logic, you can just use this one and just say, by having more blue dye in there, there'll be more molecules, so it'll take longer for the bleach to oxidize it.
If you explained it with just the thing about 0 order, without the having more to oxidize thing, would it still be right?
As long as you could say, since it's 0 order increasing, but you still have to say, and so increasing the blue does not speed up the reaction, it'll just cause it to take longer for the OCl minus to react with all the more molecules present. So, but yeah, that would work. Okay? And then, was there a C to this one?
Yes.
What's C say?
It's basically saying...
Is it long?
You want to do the red food coloring? It's the red food coloring.
Oh, the red. Oh, yeah, so you changed to red. So what's the one thing you have to do?
Wavelength.
Change the wavelength. That's going, hey, that has nothing to do with kinetics. Now they're asking you a lab question about the spectrophotometer. Okay? So again, we can't have tunnel vision, so it's not really, so the one thing, if you change from a blue to a red, you just got to change the wavelength because it's going to absorb at a different wavelength. Okay? So if you want on that one, make a note, Beer's Law, as well as that. So C is really a Beer's Law question, or a Spec 20 really question.
Yeah,
right?
but
Based upon the Beer's Law lab that we did.
If they ask about spectrometers or photospectroscopy, is that what's going to be about, like Beer's Law?
Usually a spectrophotometer, yeah. It's going to be the same prism. Now, and also, just note that there's another piece of equipment that's very similar, and it's more of a probe that we can use with the LabQuest. And it's called, colorimeter. It's a colorimeter. Does basically the exact same thing as a spectrophotometer. It measures the change in color from a dark color to a lighter color, does the same thing. So if it's a colorimeter or a spectrophotometer, it's going to be the same thing. Okay? So now here's this one. Again, we have the 3 graphs. The rate of the reaction is studied at 625 in a rigid reaction. 2 different trials, each with a different starting concentration, were carried out. the data were plotted in 3 different ways as shown. So we have to go through and look at our 3 graphs. Whoops. And once again, which one do we look at? Okay, it's hard to see, but which ones we look for the straight line. So which one, and some of this is a little tricky because that's not very curved, but it is still curved. In the first one you can see more. So it's the same experiment, just 2 different trials. So if one of them's curved, both of these are within experimental data straight line. So since it's 1 over, what order is it? Second order. Okay? So we know it's second order. Now, looking at, all we're doing is vaporizing. So, for trial 1, calculate the initial pressure in atmospheres in the vessel at 625. Assume that initially all gases present, all the gas present is C4H6. So in other words, before anything starts, you use C4H6. We want to know what's the pressure. Ding, ding, ding. PV equals nRT. Okay? So, but they don't give us all of that. So PV is equal to nRT, but I want pressure, so it's going to equal nRT over V. Now obviously we know R. Do we know the temperature?
Yes.
Okay? So we need moles and volume. So how do I get moles and volume? Okay? Moles per liter is also what? Molarity. So, now, we want, okay, listen, this is important. Because, so which graph do I go to?
Any of them.
Any of them, but if I go to this one, then I'm going to have the log of concentration. So I have to find actually concentration. So I would have to, take E raised to the negative 3.9. That's a lot of work. But this one is just what? Concentration. Where do I want to go to? Which dot do I want to go to? Okay. I'm almost done. Okay. So which dot do I want to go to? Up here. That's my initial concentration because I want to know what's there initially. So it's 0.02 moles per liter. So notice that we can actually change this to pressure is equal to mRT. Molarity times R times T. Now, because N over V is moles per liter, which is molarity. Okay? So you can either plug in the 0.020 moles over 1 liter, or just know this. And by the way, this is what same thing as remember we did osmotic pressure real quickly. Pi, the osmotic pressure is equal to mRT in a solution. So it's the same thing. So we just find the pressure is equal to 0.020 times, use 0.0821 times the 625K. So the pressure, in order for it to come out in atmospheres, did it ask for atmospheres?
No.
Yes.
1.03.
1.03 ATMs. Okay? So again, it's talking about all gases. And so it gives you a pressure and a temperature. So I'm going to want to always think gas law. Now, it may not always work, so then you got to go to plan B, but in this case, it worked. But you need to know again that pressure and concentration, moles per liter. Because we may not have ever used it when we're doing gases, we generally don't use that MRT version of it. Okay? So, so now it says, use the data plotted on the graph to determine the order of the reaction with respect to C4. So we already did that. So we know it's what? Second order because
Oh, linear graph.
1 over concentration versus time is a linear graph which is in accordance to a second order reaction based upon the integrated rate law. Okay? And then C, the initial rate of the reaction in trial 1 is 0.001 moles per liter.
I have a question. For B, it doesn't even say like explain or anything. So can I, like?
That's true. It's probably a 1 point. This is only a 4-point question. Okay? So you probably just, all you have to do is say second order. You know?
Can we just say like 1 over the concentration times time is linear, or 5 versus time is linear?
It's linear.
That's all we say?
And so, yeah.
Second order? It's
For,
second order?
which means that the reaction is second order.
Okay.
Or which indicates, or, okay? Now, again, that's where I say, if you want to be gung-ho, you can say based upon its integrated rate law. Now, so listen. So we need this, so it's second order. Okay, so how do we do C? What equation do we use? Okay?
Rate law. You have the rate.
Right.
You have the
Okay.
rate law.
Well, it's second order.
The second order is only one thing.
So rate is equal to K times the constant is C4H, C4H6, but it's second order, so it's going to be squared. So they tell you the rate.
Yeah.
They tell you the rate is 0.0010 molarity per second is equal to K times the initial concentration. So what do we put in here? 0.020. And that's molarity squared. So what's the numerical value? Just 2.5, not times anything? And what's the unit going to be? Okay, but just in terms of molarity. So you got molarity squared and a molarity.
So,
Over molarity times everything.
It's a lot easier just to do it that way than trying to do, see, because what this is equal to 2.5 over moles per liter times seconds. Right? So moles per liter, when you divide by a fraction, you invert and multiply, so that turns to be 2.5 liters per mole seconds. But I think it's just easier to do it in terms of molarity and just leave it in that, and that's 100% correct. Okay? So you can, rather than trying to do the reciprocal and all
You don't
that.
have to match their units and all that?
There's on the guidelines they give you answers, but there's always more than one answer. Okay? Just hold on. Just hold on. Okay. So, very, very doable. We need to understand collision theory. What makes an effective collision? The 2 criteria for an effective collision, and how the 4 factors of concentration, temperature, surface area, and catalyst all affect how it's going to have an effective collision. To be able to explain that on a free response question like these. We need to be able to do calculations using both the differentiated rate law and your integrated rate law. Okay? I think you're pretty comfortable with the math part as well. The little tricks of the trade are half-life. If the half-life remains constant throughout different trials, that means it's first order. If it varies, it's probably second order. We need to be able to understand our graphs and be able to know what zero order, first order, second order graphs going to look like. I think y'all are pretty comfortable with that. We do need to do 2 more types of practice problems, and we'll focus on that on Monday, is that we need to do a couple of more where we have that fast equilibrium and have to do that proof. Okay, and be able to do those substitutions. So we need to practice some of those. I think there'll probably be some in the Princeton Review that you do tomorrow. In addition, we need to be able to look at what happens if one of the reactants doesn't stay constant in our table. All right, how do we solve for X and Y if only one of the reactants, A and B, if one of them is different every time? And it's a simple little math thing. It's not hard.
So like the actual
Yeah, so in your table, in your differentiated rate law, when we're dealing with concentrations, normally, there are at least two experiments where A stays the same and B changes. And then B stays the same and A changes. Well, there are cases where A stays the same and B changes, but B never stays the same, and you still have to figure out A. Okay? It's just adding, it's really quite simple, but we just need to do a couple of practice that. So on Monday, what we're going to do, I'll go over these last three questions that we're working on, 87, 89, and 2000, which is what you're going to use the rest of the period to work on. If you finish, find something else to do and just stay quiet. Okay? I'll go over those and give you credit. Actually, what I'll do is I'll look at all six. I'm going to look at all six on Monday, along with Princeton Review. And the Princeton Review is I think it's big. I have the pages on the instructions there, but it's the big idea 6, and it's the whole chapter is just kinetics. So it's not like we know sometimes we have to break it up. So you got to do the whole thing, and it's going to be relatively long. Okay? So we need to do all of that tomorrow. So you have 6 questions, these 14, 15, and 16, along with these 3. I'm going to look at those on Monday, and I'm going to look at Princeton Review, and I'll answer any questions. We'll talk about those 2 other things we need to focus on, and then we're done with kinetics. Okay? Hopefully then I'll have some time then to introduce equilibrium. We'll talk about equilibrium on Tuesday and Wednesday. We might even do a lab like on Tuesday with equilibrium. I'll see how we get on Monday. Thursday will be the test on kinetics. I won't be here. Okay? And then we're just going to go from there. All right? All right, so that's what we got.